Thank you.
Yeah, big screen.
Thank you, Professor.
You're welcome. The forum is yours.
Hello, everyone. My name is Hao Zhong. I am from the Hefei University of Technology. I am very pleased to be here and to join this conference. Today, the title of my presentation is Adaptive Filter Remote Scene Image Segmentation Network based on attention mechanism. As is shown in the picture, and the main parts of my research are about deep learning for remote scene image segmentation. Okay, and let's first introduce our background and related work. As we all know, image segmentation is a pixel novel classification, and its purpose is to separate the objects we are interested in from the whole image. And compared with general image segmentation, remote scene image segmentation is more challenging. It is many faceted in following problems: a large scale variation, a large intra-class variance of background, and foreground-background imbalance. These factors make it difficult for the network to accurately locate and identify the foreground features of remote scene image. Okay, the next part is our method. This figure shows our final model on AIRCC data. The backbone of our network is a link net. Firstly, we apply as a proposed anti-aliasing module AFM before each downsampling operation in the network. Then we insert the RFM module to eliminate the semantic gap between the corresponding levels of encode and decode. Thirdly, in the intro part of the network, the GAM module is added to aggregate a multi and scale context information, while also avoid redundant information of background. Finally, the function of mode is used to classify the output of the network. Currently, the research on remote scene image segmentation is mainly based on deep learning method of convolutional neural network. Downsampling is an important part in CNN. It can greatly reduce the number of parameters and computation. However, it will also cause aliasing. This aliasing refers to the phenomena that high frequency information in a signal is destroyed during subsampling. Therefore, without proper anti-aliasing techniques, a subsampled signal can look completely different compared to its port. To address this problem, we insert AFM before each downsampling of encode part, and AFM is shown in this picture. we can see from we can see through convo, batch normal, and reshape operations, filters can dynamically generated in each spatial position and each group of channels to avoid aliasing. For the larger scale variation and foreground-background imbalance in the remote scene image, we propose GAM and global attention model. As is shown in this picture, the context information of different scales can be fully captured by the dilated convolution with different rates. Then the context information at different scales is multiplied with the originally high features extracted by CNN and in a pixel-wise manner after going through convo one by one, so as to constitute attention in spatial dimension. In addition, the global information of the object is adaptively captured by GP and global polling, and convo one by one operation are another branch of GAM. Skip collection. Skip collection are widely used in encode and decode structures. Loss of spatial information can be reduced by skip collection. However, the information of the encode part is of a low level, while the information of the decode part is more high level. And therefore, there may be a semantic gap between the corresponding levels of encode and decode. For this problem, we induce a residue fusion module on the skip collection. The module structure is shown in this picture. Firstly, we reduce the number of channels through one by one convo to avoid the redundancy of calculations. Then the low-level fusion is learned through 2 3 by 3 convos to reduce the semantic gap between the encode and decoder. The last part is the results of our experiments. We evaluate our approach by conducting experiments on 2 datasets. One is the deep global road extraction. The other is an area image labeling. And let's take a look at the experiment results. And Tab 1 shows the test results on road datasets. On road dataset, we use Reslet 18 as our mode encoder when we conduct ablation studies on AFM. Through grouping experiments with different channels, it is found that as the number of groupers increase, the filter performance of the network gradually improves. When G equals 8, it reaches the optimum. The number of groups still increases. The performance may be degraded due to the overfitting of the network. Of course, there could be other reasons. To verify the road segmentation performance of the model, recall and F1 score are used as evaluation indicators. The results are shown in Table 2. Compared with the original Nicknet 34, our final model increases the recall and F1 score by approximately 3.2% and 3.6% respectively. And the test result of deep global road extraction is shown in the picture. From left to right, it is the input image, ground truth, and Nicknet 34 segmentation result, ADGAM segmentation result, ADIFM segmentation result, and the final AIRCC segmentation result. Among them, white represents the road foreground object, and blank represents the background. From the picture, we can know that our final model, the AIRCC, improves the overall road segmentation and can make the road more connected. And the ablation experiments of different networks on road dataset are shown in Table 3. And F1 score is used as the evaluation index of network performance. The F1 score of our model on AIRCC can reach 82.67%. The next is a result on building datasets. To fully verify the segmentation and performance of each model, ROU and F1 score are used as the evaluation index for segmentation, as shown in Table 4. The final network, AIRCC, is about 4.3% and 3.2% higher in ROU and F1 than the original Nicknet 34. The test result of area image labeling are shown in this picture. And compared with the original Nicknet 34, our final model AIRCC can improve the edge segmentation of small buildings. It can be seen from the figure that the result of segmentation of building information has more regular, smoothing, and complete. Okay, it has been my pleasure to give you my viewpoint, and that's all. Thank you very much.
Thank you. Thank you very much for the presentation. The presentation is great. Are there any questions from forum?
No, thanks. I have no questions.
Yep. Are there any questions from other fellow researchers?
Yes. Our this paper is have any other authors, including my tutor, Cong and my other student in the lab.
Yeah, it's okay. It's okay. Thank you. Thank you very much. It's a great presentation. Yep.
Okay, thank you very much.
You.
Thank you.
Yep. Can I invite